This last video on nuclear reactions and our chapter 16 look at radioactive materials is going to focus on nuclear fission and one of the primary applications of nuclear fission, which is nuclear power. So let's look at nuclear fission first. What is it? Well, nuclear fission is an artificial decay of nuclear reactions. So we usually think about nuclear reactors as being these spontaneous decays where a radioactive element shoots off a particle, and the result of that decay is energy and in some kind of either a particle or a wave of electromagnetic light or both. In nuclear fission, we do this artificially by taking an unstable isotope and bombarding it in some kind of way to get it to spontaneously split into multiple nuclei. And when this happens, lots of energy gets released in the process. And in addition to that, we also get more neutrons. Now, the part that's important there is those neutrons. So one of the more common ways that this occurs is we have an unstable nucleus of uranium. That unstable nucleus of uranium we shoot neutrons at, and the neutrons get absorbed by that nucleus. And so for a brief moment in time, this already unstable nucleus of uranium-235 gets turned into an even more unstable nucleus of uranium-236. And that unstable nucleus of uranium-236 is so high in energy, so unstable, that instead of just breaking off into an alpha particle or a beta particle or even a gamma particle, a gamma ray, it actually splits. The nucleus breaks apart into two smaller nuclei. In this case, one of barium and one of krypton. And in addition to those new nuclei, what we get is a high amount of energy. Energy comes in the form of multiple gamma rays. So not just one gamma ray like we see in gamma decay, but multiple gamma rays that are being shot off in this high energy reaction. And we get the ejection of 3 new neutrons that can go out and eject themselves into another nucleus of uranium-235 and repeat the process over again. And so what happens in nuclear reactions like these is that they become self-sustaining at a certain point. And depending upon how well they are self-sustaining, that's where we can get into some problems associated with nuclear reactions and nuclear power. If a critical mass is present, that is enough that the self-sustaining reaction grows out of control, then what we have in that particular situation is something akin to an atomic bomb. So this reaction, when harnessed appropriately, can become one of the more powerful ways that we can actually do nuclear reactions. And so the most common application of this is of nuclear power plants, where that energy that is produced gets harnessed. And the way that it gets harnessed is the abundant heat that is created through the nuclear reaction gets trapped. We trap that heat, we turn that heat into usable energy by using it to heat water. The water turns into steam. The steam can then turn a turbine. The turbine then turns a generator. And that captures and traps the electrical energy until it is needed. Now, nuclear power on The Simpsons aside, an actual nuclear power plant looks something more like this, where we can see that we have our zone here. We have a steel vessel that contains a number of the zones. We have a stack. Here are our water tanks and the control room. So this is actually where Homer sits. And inside of the zones here, we have our water that is placed into the reactor, pumped into the reactor. The reactor generates the heat, pumps the steam into the electrical turbines here. The turbines are then turning the generators, and then the generators get turned over to transmission lines, which can then take the energy and through transformers push that electricity out to the people who need it. Once the reaction is completed, then the fuel rods are held in this storage pond here, and they contain the somewhat used uranium, or once the uranium is completely spent, then it goes into the waste tanks down over here. And so a nuclear power plant is very, very complex in its arrangement, even though the reaction is quite simple. And so in addition to this discussion that I'm having here, I'll also put a couple of links here um, in the description of how nuclear power actually works in a little bit more detail, which will come in handy with some of our later assignments. Now, what's wrong with nuclear power? Why do we have such hang-ups about it as a society? Well, one of the reasons we have hang-ups is because the spent nuclear fuel is still often radioactive. In fact, a lot of times it's radioactive and has very long half-lives. And those spent fuels can have, a lot of associated radioactivity with them. Storage can be a difficult task because a lot of the containers that we would like to hold them in are susceptible to corrosion. And as being susceptible to corrosion, there are ways that the spent nuclear fuel could get out and potentially get into the ground, get into the water supply. And the other main issue is that systems malfunctions can lead to criticality. So when a normal nuclear power plant is running and running efficiently, the amount of fuel that is being used is well below a critical mass. And that's an important part of the reaction. When we have a critical mass, as I mentioned before, we have this capability of having more or less an atomic bomb. But when the plant is operating properly, we're well below a critical mass, so that part of the problem isn't really something that we have to deal with. But if something goes wrong, if there's a systems malfunction, then there can be enough fissile material present to start a chain reaction, and that's when things can kind of go awry. And there are a couple of nuclear disasters that are associated with just that kind of thing happening. So we go to 1979. 1979, 3 Mile Island, Pennsylvania. The coolant that is used to modulate the heat, to make sure that the heat doesn't get too out of control, escapes and ejects radiation into the surrounding area. Now, by all intents and purposes, 3 Mile Island, while a disaster, was pretty good. There were no fatalities. There were some lasting effects in terms of the link to increased cancer risks for those people that lived in the area. But in terms of overall risk, though, the primary damage with 3 Mile Island was political. Since 3 Mile Island, there have been very few new nuclear power plants built in the United States other than for strictly research or military purposes. And that poses a different set of issues when we start to think about how technology and things have developed over the time in the past nearly 40, 50 years. Probably the most common and most well-known nuclear disaster happened in Chernobyl, which was part of the Ukraine in the USSR in 1986. Now, a lot of things were going wrong at the Chernobyl disaster. We have neglect, we have an aging nuclear reactor, we have an understaffed population, and ultimately the kind of the last pin in the grenade to be taken out was there were operator errors, and that leads to a power surge. It triggers an explosion in the reactor and a partial meltdown of that reactor as well. In the end results, we have radioactive and fuel and byproducts being released into the atmosphere, and that atmospheric cloud travels over Russia, Ukraine, Belarus, parts of Western Europe, parts of large parts of Eastern Europe. In total, 56 people died due to the explosion itself and to the high exposure of radiation. We also see the health of over 5 million people impacted immediately. And even as recently as 15 years ago, 2005, we have thyroid cancer being a significant latent effect that continues. More recent example, going back to 2011, the Fukushima disaster in Japan. Following an earthquake and a tsunami, the cooling systems fail in one of the reactors, and we get a partial meltdown in at least 3 of the reactors. Now, why it failed was the cooling system that was used utilized seawater pumps. So they were pumping in seawater from the ocean to help to cool their reactors. And when the tsunami hit, those pumps were deactivated, but they were deactivated without first shutting down the nuclear reactors. So the reactions inside the nuclear reactor continued, but they didn't have any fresh water to come in to cool down the system. And so as a result, nobody died, but there were many people, 25, that were treated for radiation, and the infants and young children were the most affected group, as each of their risks for cancer increased by at least 1%. And so we have pictures of each of these nuclear disasters. Here on the top, this is 3 Mile Island. You've probably seen this picture before. It's a very common nuclear disaster in the United States. It is our nuclear disaster. This is a picture of Chernobyl. That crater there in the bottom, that is where the power plant was. That's where the reactor was. Now, parts of this have been sealed in cement to try to lower the reactor and the radiation. This most recent picture, is from the Fukushima in Japan, and we can see that they're actually actively trying to put out the fire there to try to prevent that spread of nuclear fuel and radioactive particles in the area. Now, all three, with the exception of Chernobyl, Fukushima still is active, at least in part. The others have been deactivated, at least somewhat, or in the case of Chernobyl, obviously that one was deactivated fully due to the radiation risk. So one of the things that we will explore in this course with our critical thinking assignment is the use of nuclear power. And so I will be posting a video shortly that outlines that critical thinking assignment. But for now, this is it for our exploration of radioactive materials here in Chapter 16. If you have any questions, please feel free to reach out to me. But otherwise, I'll see you later. Have a good day.